Okay, so we've got this circuit here. We've got a battery, a capacitor, a couple of resistors, and this wiring set up here. It also tells us voltage of the battery. Both of the resistances are the same, and we know the capacitance is 1 farad, and the capacitor is initially uncharged. And we've got this arrangement of unconnected points here that's basically going to act like a switch. We are free to choose how we connect those together. And it says at time 0, a wire is connected from point A to point B. So we're going to connect these here. And that forms a complete loop. So current's going to start flowing. And what would you expect to happen here in this loop?
That loop would be complete through the capacitor, the battery, and resistor 1.
Yeah, we've got current flowing through those elements. It's flowing through the battery, the capacitor, and resistor 1. And since that's just one single loop, that means it's going to have just one value of I, one value of current associated with it. So we can just say there's a single current, and we don't know what that is. Also, since we've got this capacitor and resistor, we can expect the current's going to be changing as time passes. So we should really write I as a function of time. And can we write out a loop rule equation for that? If we've got all those delta voltages, so all these delta voltages, the battery, resistor 1, and capacitor, that's a loop, so they have to add up to 0. What formulas could we use for these, though? Like, for instance, a battery always has what voltage?
Epsilon?
Yeah, that's just this constant plus epsilon. I'll just write that as E for now. And what about a resistor? Voltage of a resistor is going to be what? For any resistor, what's the delta voltage formula?
Negative IR.
Let me put the chat over there. So we can always fill in a negative IR for the resistor. And then what about for a capacitor? Do we have the formula for voltage of a capacitor?
Q over C?
Yeah. And generally we treat that as negative Q over C because it's really a pushback against getting more charge. So there's our loop rule. Epsilon from the battery plus negative IR from the resistor plus negative Q over C from the capacitor equals 0. And it's also often convenient to just add those negative terms to both sides. So we get epsilon equals Q over C plus IR. Essentially signifying that the battery is doing two things. The battery's voltage is causing charge to be stored in the capacitor, and the battery's voltage is causing current to flow through the resistor. It can do some of each, or it can do a lot of one and none of the other, or vice versa, but it can't do lots of each, and it can't do none of each. Those two terms, something about the current and something about the charge, have to add up to the constant voltage, 40 volts. Any questions on that so far? And under those circumstances, if we're in the process of charging up the capacitor here, and in general, anytime we've just got this loop with a capacitor and a resistor, and in this case, a battery, how would we find the half-life? Do you have an expression for how long the half-life should be in cases like this?
Tau times ln2?
Yeah, it's just the time constant times logarithm of 2. And yeah, the time constant is itself is just R times C. R times C times logarithm of 2. And we know the resistance, we know the capacitance, so we can just multiply those together. We've got a resistance of 14.42. Is that 14.42? Yeah. So resistance 14.42 ohms, capacitance 1 farad, and logarithm of 2. So if we multiply that out, we get 14.42 times 1 times logarithm of 2. And that's pretty close to 10 seconds, because ohms times farads is seconds. 9.995, we'll just round that off to 10. So it takes 10 seconds for the current to drop to half the original value. It takes 10 seconds. The charge is increasing towards a non-zero asymptote. So it takes 10 seconds for the charge to go halfway towards the asymptote from where it is now. Any questions on that so far?
How do you know when the value of like delta V capacitor is positive or negative? Because I think there was like another problem that I was doing, and the capacitor was like positive, and we had to do like a problem similar to this.
I would generally always write the formula for delta V of a capacitor as negative Q over C. Sometimes that works out to be a positive value because the charge is sort of arranged backwards on the capacitor. Which side of the capacitor is high voltage versus low voltage is really about which side has the positive charge and which side has the negative charge. But in terms of the equation for purposes of the loop rule, I would write it as delta V equals negative Q over C.
Okay, so there could be like a possibility where the capacitor is also like pushing a current if it's pushing a current in the same way and it's charged.
If the charge on the capacitor is arranged so that it's pushing in the same direction as the battery, then you would treat the capacitor as having a positive value for delta V.
Okay.
Again, you would still write the formula as negative Q over C. It's just that if the charge is arranged backwards, you would treat Q as a negative value.
Okay.
But the formula for delta V of a capacitor is negative Q over C.
Oh, so if it was working in the opposite direction, then you're saying that Q would be a negative value, so it would be like negative, negative.
Yeah, exactly. In the same way that the formula for delta V of a resistor is always negative IR. But if current's flowing in the direction opposite to the direction you're calling positive, then I itself is a negative number, so delta V becomes positive.
Okay.
And that's really all just a matter of which direction you're calling positive and which side is high voltage and which side is low voltage. But in general, anytime you've got current flowing through a resistor, the current is going to be flowing from the high voltage side towards the low voltage side. And anytime you've got charge on a capacitor, the plate with positive charge will be high voltage and the plate with negative charge will be low voltage. Any other questions on that so far? All right, and then at part B, we're looking at what's happening 20 seconds later. At 20 seconds, what's the magnitude of the voltage on the capacitor? For this, we might want to take a look at, since it's an exponential decay situation, we want to take a look at what value does it start at and what value is it approaching? Because those are really the most important things for any exponential decay situation, the starting value and the asymptote it's approaching. So what's going on at time 0? How much charge do we have on the capacitor at time 0?
Are we looking at delta VC?
The voltage or the amount of charge. What did it tell us about the capacitor's state at the very beginning?
That it's uncharged.
Right. If the capacitor is initially uncharged, so Q initial is 0. And if you plug in 0 for Q in the delta V capacitor formula, you just get 0 volts. So delta V initial is 0. The capacitor starts with no voltage at all. But if we take a look at the after a long time situation, because that's where we get the asymptote, eventually the capacitor is going to be full, which really means how much voltage? What should we assume about the voltage on the capacitor after a long time?
Equals
becomes 0?
40?
Sorry, what was that?
Wait, wouldn't the capacitor get fully charged from the battery, so it would be 40 volts?
Yeah, it should be eventually 40 volts, matching the voltage of the battery. We should expect the current to eventually become 0 because if we go back to the loop rule equation we were looking at earlier, epsilon equals Q over C plus IR. After time, as time passes, the current flows, so charge accumulates on the capacitor. That means Q increases, so current has to decrease to balance it out. Eventually, you get to a point where charge is getting closer and closer to some maximum value, and I gets closer and closer to 0. Eventually, you get almost no current at all. It's never truly going to reach 0 because it's an asymptotic exponential approach, but it gets close enough to 0 that it may as well be 0. So eventually, we have essentially no current and so much charge that without current, Q over C equals epsilon. So we can assume that eventually the voltage on the capacitor is the voltage from the battery. Eventually, delta V final is about 40 volts. And strictly speaking, this is an absolute value. It's really going to be delta V of the capacitor is negative 40 because it's exactly enough to cancel out the battery. But we're just looking for absolute value here. Eventually, the capacitor has enough charge to count as 40 volts. Any questions on that so far? So it's going to be approaching 40 volts, but it doesn't have enough time to get there. We're only waiting 20 seconds. We're not waiting a long time. So if only 20 seconds pass, how could we figure out how much the voltage has changed, how close it has gotten to 40 volts over the course of only 20 seconds?
Do we use like the half-life?
Yeah, how many half-lives is this?
Oh, it's 2.
Right, 2 half-lives. And what does 1 half-life mean? 1 half-life is the amount of time for what to happen?
Half the current.
Half the current. And also, what should we expect to happen to the voltage of the capacitor?
Increases.
It's going to increase. Specifically, it's going to increase halfway towards the asymptote. So at time 0, we've got no voltage on the capacitor. After 1 half-life, we should expect to decay halfway from 0 towards 40. So if we look at this 1 half-life at a time, zero volts changes to what would be halfway towards 40 volts? If you start at 0 and you're approaching 40, what would be halfway there?
Or 20.
Yeah. So over the course of the first half-life, that is from 0 seconds to 10 seconds, 0 volts changes to 20 volts. So after the second half-life, which would be 10 seconds to 20 seconds, 20 volts changes to what would be from there halfway to the asymptote.
30 volts.
Right. And then after one more half-life, we go halfway from 30 to 40, so we get to 35. Then halfway more will be 37.5. And we just keep going halfway towards the asymptote from wherever we are now.
So the asymptote here is
that?
40? So the asymptote here is 40?
Yeah, because that's what the voltage is approaching after a long time.
Oh, okay. And it isn't negative, or?
Strictly speaking, it would be negative because delta V capacitor is going to be opposite to the voltage of the battery. If we go back to the original loop rule equation, eventually delta V of the resistor is going to be 0 because after a long time, we can assume there's no current flowing.
Right.
So after a long time, delta V of the capacitor has to be canceling out delta V of the battery, so they add up to 0. Voltage of the battery is plus 40, so voltage of the capacitor is going to have to be minus 40. but we're just looking at absolute value here.
Okay.
Any other questions on that so far? So we know that at the 22nd instant in time, the voltage on the capacitor is 30 volts. And then in part C, we're changing the situation. We're going to be removing the wire connecting A and B. And instead, we're going to connect point A to point C. So if we now connect A and point A and point C, we now have a different circuit. In fact, we can now ignore what part of the circuit?
The battery?
Yeah, the battery. This entire branch is effectively not even there anymore because it's no longer part of the loop. The loop now consists of the capacitor, and the capacitor is now charged. We're now going to have charge on the capacitor, and the positive terminal of the battery should connect to what becomes the positive plate on the capacitor. So let's assume now that we have positive charge on one plate and negative charge on the other plate. So we've got charge on the capacitor, and this is going to cause current to flow. Current's going to flow from the high voltage zone towards the low voltage zone. And since we just have a single loop, we just have one value of current, but it's changing as time passes. So again, we have current as a function of time. We still have capacitance and resistance. There's no longer a battery, so this is going to be discharging instead of charging. Any questions on this so far?
Could you explain how you knew that it was going to be going in that clockwise direction?
Yeah, if we go back to the battery that we had in the first place, the positive terminal of the battery is going to cause the plate most directly connected to it to fill up with positive charge. The negative terminal causes the plate connected to it to fill up with negative charge. So we know we're going to have positive and negative charge on the capacitor arranged as shown here. Positive on the top plate, negative on the bottom plate. And current is naturally going to flow from the high voltage zone towards the low voltage zone. The positive terminal of the capacitor has high voltage. The negative terminal of the capacitor has low voltage. So current's going to flow from the positive plate towards the negative plate, because the capacitor in this case is what's instituting that push. Without any battery, the capacitor is just going to push charge out of itself. The thing is, though, the direction of charge, the direction of current flow doesn't really matter here. If all we care about is how is the voltage changing, we don't need to know which direction current is flowing. We just need to know that current's going to flow in the direction that diminishes the charge of the capacitor. The capacitor is discharging here. Any other questions on that so far?
If we didn't know that there was a battery there before, then there would be nothing to charge up the capacitor, and there would be no charge through the entire circuit.
Yeah, if the capacitor was empty in this case, then nothing would happen. If you just take an empty capacitor and connect it to some resistors, you don't get any current because there's no push causing it to flow.
So then if they posed the, like C first, then, and we didn't, they didn't connect A to point B first, then this can't happen, right?
Right. If we just connected A to C at the very beginning, then no current would flow because there's no voltage source. There's nothing causing a push.
Okay, thank you.
Mm-hmm. In this case, though, we know that there is at the 20-second mark there has been enough charge accumulated that we have 20 volts. So we can treat delta V capacitor initial as 20 volts, which means there's 20 volts available for making current flow. At this point, our loop rule equation would look like almost the same, except we don't have a battery. We just got delta V resistor plus delta V capacitor equals 0. And if you fill in the negative IR and the negative Q over C, and then solve for one of those terms, you could get Q over C equals negative IR. So we get current flowing because there's charge on the capacitor. As soon as there's no charge, there's no more current. But they're proportional. The more charge there is on the capacitor right now, the faster current's going to flow. And so this also leads to exponential decay. In this case, though, if we want to list out starting and ending conditions, we start with 20 volts. After a long time, what's going to be the final voltage of the capacitor?
0.
Yeah, it'll eventually diminish to 0 volts because the charge is draining. Eventually, you're going to end up with no charge at all, or at least close to 0 charge. It's going to be an asymptotic approach. And to figure out how fast it's decaying, because ultimately we want to graph this. We want to graph delta V for the capacitor, starting at 20, decaying towards 0. But we want to figure out how fast that occurs. So how would we calculate the new half-life here? Or would the half-life be different?
Would the half-life not be a different value? Or actually, it would be a different value because the R is different, right?
Yeah, we can still use the same formula, R times C times logarithm of 2, but the total resistance has changed. Half-life is still going to be R times C times logarithm of 2. But what's the new total resistance here?
Is it just 14.42 times 2?
Yeah, because we've got 2 of these resistors in series, so we can add together their resistances. So total resistance now is 28.84 ohms multiplied by the capacitance, which is still 1 farad, times logarithm of 2. Since we've just doubled the resistance but kept everything else the same, that's going to end up doubling the half-life. So the new half-life, instead of being 20 seconds, or instead of being 10 seconds, is going to be 20 seconds. So we should expect it to take 20 seconds for the voltage to decay halfway towards the asymptote. And in this case, instead of starting at 0 and decaying up towards 40, it's starting at 20 and decaying down towards 0. So we now know, I think, everything we need to know about the voltage. It starts at 20 volts, and every 20 seconds, it drops halfway towards 0. Any questions on that so far? Then let's see if we can draw out that graph. I'm going to tidy things up a little bit. And I think we're going to have to be careful about this graph here, because this graph is listing not just times after we change the wire. We're listing times from 0 to 80 or whatever. And at what time does something important change? What was
20 seconds?
Wire? Yeah, 20 seconds, right? So at 20 seconds, we've got this very important change happening. I'm going to put a mark on the graph representing that. So at time 20 seconds, everything changes. So before 20 seconds, we're charging. After 20 seconds, we're discharging.
Wait, why are we charging before 24 or 20 seconds? Because I thought like, is that
Part B suggested, or Part A suggested that you connect the wires from A to B. So you're including a battery in the loop. That's charging it out.
Oh, okay.
Then at 20 seconds, you remove that wire and put it in a different orientation so the capacitor is going to be discharging. And we know that over the course of the first 20 seconds, let's put in some data points here. We know we have, it started off uncharged. So it starts off at 0. And then at at 10 seconds, we found that it was changes from 0 to 20. So after the first half-life, while it's charging, it charges from 0 to 20. And then over the course of the second half-life, from 10 to 20, 20 volts decays towards 30 volts. So our initial approach is going to look like this. And if we continued, we'd end up going from, over the next 20 seconds, it would go from 30 to 35. Then over the next 20 seconds, it would go, or no, next 10 seconds, I should say. Next 10 seconds, it would go from 30 to 35. Next 10 seconds, it would go from 35 to 37.5. And then halfway and so on. But it never actually gets there because we interrupt the process at 20 seconds. So we could actually draw this in. We could draw in a smooth curve connecting these data points. And let's see what that would look like. If we just draw a smooth curve connecting these, smooth curve. Something like that. And this would keep going higher and higher and higher, approaching the asymptote, but we interrupt the process at 20 seconds. So it just goes up to there. Any questions on that so far? And then for the discharging process, we now have 20 seconds as the half-life. So it takes 20 seconds to decay halfway. And since it's starting at 30 and dropping from there, what would be halfway towards the asymptote? If you start at 30, decaying towards 0, after one half-life, what would be halfway from 30 towards 0?
15.
Yeah. So at that time, after one half-life, which is 20 seconds, because we were talking about the discharging cycle, so the half-life is 20 seconds. So 20 seconds later, which would be at 40 seconds, we're going to be at 15 volts. So 40 seconds matches 15 volts. So we can put a marker there, 40 seconds, 15 volts. And what about one half-life after that? If we wait to 60 seconds, one half-life later, what would be halfway from 15 down to the asymptote?
$7.5.
Right. So after another half-life, another 20 seconds forward into the future, we're going to be at 7.5. And then one half-life beyond that, if we take it all the way to 80 seconds, we'd be halfway from 7.5 down to 0. So half of 7.5 is what, 3.75? So we're around here. So we get more and more data points. Every, I guess that should actually be one more further out. Yeah. One more tick mark further would be 3.75. So we now have more data points. Every 20 seconds, it drops halfway, halfway, halfway towards the asymptote, which in this case is 0. Any questions on those data points so far?
I have a quick question. Regarding the delta V, like capacitor initial value, should it be 20 or 30? That's the part I'm confused on.
Well, at 20 seconds, we start off at 30 volts. Because during the charging portion, every 10 seconds, we decay halfway. So for the first 10 seconds, we decay from 0 to 20, because that's halfway towards 40. Over the next 10 seconds, we decay another halfway towards 40. Halfway from 20 to 40 would be from 20 to 30. So at the 20-second instant in time, the voltage on the capacitor is 30 volts. Since we interrupted it at that point, it stays at 30 volts until we start discharging, and then it decays towards 0. So the final result of the charging portion becomes the initial state of the discharging portion. Any other questions on that so far? And then we should be able to connect those with an exponential decay curve. It's decaying downwards towards 0, so it should be looking something like, it doesn't look so great. Try that again. That works pretty well, except for that second spike. Something like that, decaying towards 0. And so if we draw in that graph, we can use that to predict what the voltage will be at any time we want. We could get even more accuracy if we use the idea of time constant to put in a few more data points. But this should be the general idea, decaying upwards towards 40, but never getting there because it's interrupted at 30, and then decaying from 30 towards 0. Any other questions on that graph? All right. Then let's take a look at one of the other examples. Let me pull up that. One moment. Let's try this one. Can you see this one all right? With the two tanks of water. So we've got these two identical tanks of water connected by a thinner pipe, and one of them is raised up by 4 centimeters.
I don't see the question.
Is this not showing up?
I just see the part C at t equals the same graph as before, except there's nothing on there.
Oh, it's still showing the same as
question, yeah, just without the rating.
Is that all right?
Yeah.
Okay. All right, so we have, we've got these two standpipes or two tanks that are separated by or connected by this thin pipe. We lift one of them up. So previously everything was at equilibrium, they're at the same height, but then we raise one of them up. They're no longer at equilibrium. What would be equilibrium in this new situation? Or what would have to happen in order for them to be at equilibrium?
Would they have to be at like the same water level?
Yeah, we would expect these waters to eventually approach the same level. And since these are identical standpipes, well, we know in general that whatever volume of water flows out of one flows into the other one. And since they're the same cross-sectional area, what does that tell us about the height changes? Like let's say water flows out of the left tank, so it drops by 1 centimeter. Meanwhile, what happens to the right tank?
It'll increase by 1 centimeter?
Yeah, that water level goes up by 1 centimeter. And we usually wouldn't assume that the height changes are the same. Usually we would assume the volume changes are the same. Whatever volume of water flows out of one flows into the other because of conservation of volume. But if the cross-sectional areas are the same, then the height changes will also match because volume is just area times height. So same area means the same change in height also. So whatever this one decreases, the other one has to increase by the same amount. So if we take a look at the heights here, we know this one has to be decreasing by some amount and this one increasing by the same amount, so they reach the same absolute altitude. So if this water level goes down by some amount, let me make that smaller. If this water level goes down by some amount and this water level goes up by the same amount so that they reach the same level, what changes, what decrease and what increase would make them reach the same level? Well, how far off are the levels right now? At the very beginning, what's the difference between those two surface levels?
4 centimeters.
So how much would you have to make one go down and the other go up to make up for that 4 centimeters of difference? If you got two things that are 4 centimeters apart and you move them towards each other so they meet in the middle, how far did each one move?
Each one moved 4 centimeters, but in total would it be 8?
Well, if they're 4 centimeters apart and you move one down 4 centimeters and the other up 4 centimeters, they're not going to match. They're 4 centimeters apart. You move one down and the other up the same distance, so they meet in the middle. How far did each one move?
2 centimeters.
Yeah, each one moves 2 centimeters. So if we want them to reach equilibrium, each one would have to change by 2 centimeters. So what would be the final depths of water in each tank? If this one starts with 10 centimeters of water and drops by 2, this one starts with 10 centimeters of water and increases by 2. What are the final depths?
I'm sorry, why is it 2 specifically?
If they're 4 centimeters apart and they're both moving the same rate to meet in the middle, each one is going to have to move 2 centimeters to cover the 4 centimeter total.
Oh, okay.
So it would be 12 and 8.
Yeah. The right tank is going to increase from 10 up to 12. The left tank decreases from 10 down to 8. So we end up with a final situation that's going to be, let's see if I can draw this in. So the right tank in the final situation is going to be full to 12 centimeters. The left tank is going to be full only to 8 centimeters. But the 8 centimeter depth plus the extra 4 centimeters of elevation matches the 12 centimeters of depth on the right tank. So we've got 8 centimeters of depth plus an extra 4 centimeters of elevation. And over here, we just got 12 centimeters of depth. But 4 plus 8 is the same as 12, so they both end up with surfaces at the same absolute elevation. So that would be the equilibrium situation. Equilibrium would be when the water levels actually match each other, which means 8 centimeters of water in the left tank and 12 centimeters of water in the right tank. So those would be the final equilibrium, which means we can list out initial and equilibrium values for each tank. Left tank starts at, let's call these, we want to call these a specific variable. Let's say just H, I guess. H initial is 8, and H final after a long time, or no, sorry, H initial was 10. H final after a long time would be 8. For the right tank, H initial is 10, and H final after a long time approaches 12. So once again, we've got starting values and asymptotes that it's going to approach. Any questions on that so far? And why would we expect an exponential decay here? What is it about this situation that suggests the exponential sort of pattern?
They will get close to being like at equilibrium, but it won't like actually be exactly Like the difference in height won't be exactly 0. It'll just get closer and closer to 0.
And why is that? Why would we expect it to get slower and slower and slower as the heights approach the equilibrium value?
The current decreases.
Right. The current is being driven in this case by the height difference. The fact that the water levels are at, or the surfaces are at different levels means that there's a pressure difference. That pressure difference causes fluid to flow, or rather the height difference causes fluid to flow. So when the pressure and height all balance out, there would be no current at all. But the closer everything gets to equilibrium, the less difference there is and the less current is flowing because there's less push to drive it. So as we approach equilibrium, the current gets slower and slower, and so we're approaching equilibrium more and more gradually. So we should expect this to lead to an asymptotic behavior. And knowing the starting value and asymptote gives us most of the information we need. In fact, I don't think we really need to worry too much about the rate of decay because we don't have enough information about the flow pipe to determine the half-life. But we can use this information about starting and equilibrium values to at least sketch the graph. If we put some marks on the graph at 8, 10, and 12, so let's say here's 10, here's 12, here's 8. We want those to be pretty close to equidistant. So 12, 10, 8. May as well make that to scale. So we know both of these graphs are going to start at 10, and one of them approaches 12, the other approaches 8. So if we fill those in as asymptotes, we know one has an asymptote at 12, one has an asymptote at 8. And they both start at 10. And these should be mirror images of each other. They're going to be decaying towards their asymptotes at the same rate. One of them going from 10 approaching 12, the other going from 10 approaching 8 at the same rate. So we would expect their graphs to look something like that. Any questions on that so far? And then if we're talking half-life, we don't know what the half-life is, but it's just saying after 2 half-lives. A half-life would be the amount of time, for instance, for the tank that's increasing, a half-life would be the amount of time to go from 10 to where?
To 5?
We're not going from 10 to half of 10, though. We're going halfway towards the asymptote.
11.
We're starting at 10 and approaching 12. What's halfway from 10 to 12?
11.
Yeah. So 11 would be how much we're at after 1 half-life. After another half-life, we go halfway towards the asymptote again. So halfway from 11 to 12 would be at what?
11 and a half.
Yeah. So after 2 half-lives, the right tank, the one that's increasing in height, would have 11 and a half centimeters of water in it. And then the left tank, the one that's decreasing in height, it's decaying from 10 to 8. So after 1 half-life, what's halfway from 10 towards 8?
9.
And then halfway again?
8 and a half.
Right. So that would be going from 10 to 9, and then from 9 to 8 and a half after 2 half-lives. And if we kept going, after 1 more half-life would be halfway from 8 and a half to 8, so that would be 8 and a quarter, then 8 and an eighth, then 8 and 1/16, 8 and 1/32. It just keeps getting halfway there, halfway there, halfway there, getting closer and closer, but never actually reaching it. Any other questions on that graph? All right, perfect. Then we're out of time for today, but feel free to email me if you have any other questions you'd like to work on Thursday as more practice. Try out the trigonometry review worksheet and the vector review worksheet on mathandcheese.org to get some practice with that before we really get going on vectors. Don't forget to vote if you haven't already, and I will see you next